Hi, my name is Ozan Öner. This is my Physics 211 project. In this project, we aim to analyze and categorize noise signals, colors of noise signals coming from different sources. We are going to use a voice recorder to capture audio samples, a computer to analyze and visualize the recorded sounds using Python code, a mobile phone used as an additional recording device for capturing noise signals, and a microphone to enhance the quality of the recorded audio signals. We are first going to gather some sources from the nature, and we are going to analyze it using a Python code. Our Python code implements Fourier transformation and obtain a power spectral density graphic, which then we calculated the linear fits of the power spectral density graph and calculated the slope of this fitted line and categorized the signal according to it. And we calculated the standard deviation of the noise. One key property used in this categorization is the root mean square RMS value of the wave. The relationship between the amplitude and the RMS values varies depending on the waveform. The RMS value is a mathematical expression commonly used in physics to represent average magnitude of a varying quantity. The primary approach in this project is to categorize noise based on the RMS values of their waveforms. Uh, Now I'm going to talk about the theoretical analysis of these waves, of these noise. In nature, there is no full white noise, and at real high frequencies, it becomes pinkish, pink noisish. The rain or the waterfall is example of white noise from the nature. Leaf sounds can be an example of pink noise from the nature. The term brown noise comes from Brownian motion, since it simulates Brownian motion. The wind sounds can be an example of a brown noise from the nature. Cherenkov radiation is an example of blue noise. Since it is really hard to obtain blue noise, we do not have any experimental graphics of blue noise. This is also very hard to obtain white noise from the nature, so we do not have any experimental graphic for that. And now I'm going to talk about the experimental graphics of the noises. The experimental graphic of brown noise, it has an error of roughly 23%. The experimental slope of pink noise is minus 0.8, and it has an error of 11%. It can be seen that both brown noise and pink noise, both of their data falls in the gray shaded area, which means that we obtained some quite nice results. Since our Python code generates a relatively bad fitted line for this one, we do it by hand. So that's why there's no standard deviation for this one. And as I said, the blue and the violet noise is very hard to obtain from nature, so we do not have any graphics for them. And the novelty of this project lies in its capacity to not only identify areas affected by noise pollution, but also compare them based on the slope of the power spectral density. So we go out and recorded some leaf noise in noisily polluted areas. For example, for the construction site, the fitted slope is minus 4.7, which is very high because of the pollution, because of the noise pollution in that area. It is very loud, so we cannot hear the leaf sound. And then we go to the highway. The slope of the fitted line for the highway is minus 4.4, which is also very high, but not as high as a construction site, because the highway is very noisily polluted, but not as much as polluted as a construction site. And lastly, the slope of the fitted line for the cafeteria is minus 2.8, which is relatively very low comparing with the other two, since the cafeteria is not as much as noisily polluted as highway or a construction site. So we can barely hear the leaf sounds in this one. Now I'm going to talk about limitations and some errors. There is a noticeable decline at the end of almost each graph, which may be due to the sudden ending of the recording and the noise it emits when the recording ends. Additionally, some errors occur due to the imperfections in the microphone and the presence of unwanted noises. and also some computational errors occurred within our Python code. Uh, our Python code does not give us a very good fit line for the experimental byte noise. Thank you for listening.